Hey everybody, welcome. My name is Tom, and this is the first in a series of videos on building a game with Rust. We're going to be doing this using mostly the standard library. At least on the Rust side, we're going to be only using the standard library. Outside of Rust, we are going to have some stuff in the browser because this is a web-based game. We're going to need to use some JS, HTML, CSS, and so forth. Even on that side, though, I do plan on using WebAssembly, and we'll be using Rust to create that. Now, I'll make some assumptions that you have basic programming knowledge. You know what a conditional loop is. You've got kind of an understanding of classes, structs, maybe, and things like that. So if you don't have that knowledge, this might be a bit confusing. If you don't understand Rust or you've never used Rust, I am going to go slow enough, and I'll be covering certain things I put in here in a way that hopefully introduces you to aspects of Rust and makes it clear what things are doing, and you should be able to find a corollary in your own language that matches that. All right, so with all that said, let's go ahead and get started. As I said, we're going to be doing a WebSocket server first, but a WebSocket server is a bit complicated, so we're not going to get it done entirely in this video. In fact, we're only going to implement one part of the protocol. So I think before we jump into what we're going to be creating, which is the SHA-1 hashing algorithm, we're going to need to kind of get some background on what WebSockets are and things like that. So let's go ahead and jump over here. I do have a article on this, so if you don't want to listen to me talk for half an hour, you can just read this, or if you don't want to even read this, just jump over to the repo and just take a look at that. All right, so WebSocket protocol. With everything said, let's jump into this. It's a bit long. If you take a look at the actual specs here, we've got, I don't know how many pages this is. It's a lot. And as with most of these documents, it's got a lot of really great examples, everything you would ever need. We're not going to be implementing all of this stuff. But we're going to implement enough so that you can connect to our server, WebSocket server, with just about any client out there. So you could we'll be using JavaScript library in order to connect to our server. Okay. Now, when you connect to a WebSocket, you've actually probably connected a lot more than you think, because WebSockets kind of lie on the same plane as HTTP. So you connect to a WebSocket through your browser, and you connect to it on port 80, just like you would, or at least you upgrade the connection via port 80. It shares the port with your regular HTTP stuff. And these WebSocket protocols are existing in 4 different states. So when you connect, say you're playing some web-based game, the WebSocket connection gets made, you transfer some data, and then you close that connection, or the server closes that connection, one of those two. But unlike a web page where you just send a request and then get a response, this is continuous. That connection is kept open the entire time through multiple sends and responses. Okay, so the WebSocket protocol is going to be in these 4 states: connecting, open, closing, and closed. And these 4 states are what we're going to be building later on. But for now, we're going to concern ourselves with one small part of this connection, which is also going to be referred to as a handshake. So oftentimes a handshake is, in terms of networking, the client says, hey, I want to connect to you. The server or another client, if it's a peer-to-peer connection, will say, all right, I need to do some verification, or you are connecting to me, and what are we using to talk to each other? And then it will send the response back saying, all right, we can talk, and then the connection gets opened. All right, so in our case, normally when you go to a web page, you're just browsing using HTTP, you're requesting an HTML document, and with WebSockets, it's a little bit different. So we want to upgrade, they call it upgrade, that connection to WebSockets. So what that looks like in the opening handshake is the client is going to send a request that looks like this. So this here is the request. And let me make this a little bigger. This request is still being done over HTTP, but we have these things in here, this upgrade and this connection. So we're upgrading to WebSockets. The connection is an upgrade type. And then there's this part here, which is the WebSocket key. So on the client side, they're going to send this key, and this key is going to need to be manipulated in a way on the server side that when it's sent back to the client has got a confirmation that the server is wanting to upgrade to WebSockets. Now, the reasoning for this is really just there needed to be a way in order to get the server to know that, hey, this particular GET request is going to be a WebSocket, and I need to confirm that this is actually what the user wants to do. It's not just they've accidentally put this, this part in with a regular HTTP request. So there's this kind of validation that happens where this key gets sent in, and on the server side, we do something with it, and then we send our response back. And then the client checks that that response is valid according to the set of steps to manipulate that string that it believes. So for example, it might send this string in, and then we could have a rule that says the server will remove every other character from this string and then send that back. And that could be a confirmation, just as likely as what we're going to do. Now, the confirmation we're going to use is a bit more complicated, but you could use a confirmation like that. Okay. And it's just to make sure that the connection is being set up, or the request is a valid request. Okay, so jumping back here, we've basically got the same thing I just showed you, this here with the upgrade connection. And the difference between a regular HTTP GET request is this. So a regular HTTP GET request has things like user agent, language, things like that. Notice none of that is in here. We don't care about any of that at this point. Okay, we're not rendering a web page, and we're not worried about the language or the encoding or anything like that. Encoding means, like, I don't know if you know this, but your web pages oftentimes when they get sent, they zip them using gzip, so they're smaller as they get sent across. So you're not just sending just an HTML page, you're sending maybe a gzipped chunk of information that's related to that page and things like that. All right, so the two things we wanna worry about are the WebSocket key coming from the user and the WebSocket accept, which is the response. So this is the response that the server is going to send. And this here is created in the following way. We take whatever the user has sent us, which is going to be some base 64 encoded string. We're going to remove the leading and trailing white space. We concatenate that with a unique identifier. There's no reason for this unique identifier. It just happens to be the unique identifier. We hash it with SHA-1, the hashing algorithm. If you're not sure what a hashing algorithm is, you hopefully will by the end of this. And then we encode it using base 64. Okay. So that's about it. We're going to do these 4 steps today, and well, these 3 steps here. We're not going to do this. This will be for a later video, but for the most part, we're going to be implementing the SHA-1 hashing algorithm. Okay. Now, SHA, the algorithm 1 at least, is a vulnerable algorithm. So meaning vulnerable as in it's no longer secure. Don't use it for anything that actually is important. Don't try to preserve any information or hash passwords or anything like that with it. We only use it in this case because we're not sending any important information. In WebSockets, we're just worried about a validation process. We don't care if it is secure, whatever we're hashing or not. It's just a way to say, yes, we want to upgrade to WebSockets, and then both sides agree, and boom, you have WebSockets. Okay? All right, so let's go back and actually start some coding here. I've made a project which has 2 files in it. I've got my main file, which is the default, just comes out as print hello world. And I've got this here, With these two files, most everything's going to be done in the SHA-1.rs. All right, so let's get started. First thing I want to do is I am going to go ahead and pull some stuff. To save you from me from typing, I'm going to be just kind of copying and pasting this and explaining it as I go. So inside my SHA-1 file here, we're going to have this basic setup. If you're not really used to using structs, if you don't know what a struct is even, you can basically think of it as it's a data type. Okay? So it's like a class, if you want to think of it like that, from Java or something. It's not a class in the sense of what it can do, but it's a class in the sense that it declares a data type. And if you haven't seen this in Rust, or you haven't seen this particular thing, maybe you're a C programmer, and you're like, oh, this is kind of interesting, we have this separate block with a function that seems to be associated with the struct. I think you can do that in C with some pointers. People don't really do it. In C++ where you have classes, or Java where you have classes, you don't have these separate impl blocks, which is an implementation block for this particular struct. So this defines a type called SHA-1, and I could have more stuff here like this, and then I could put some fields in here, variables. But for the most part, we don't have any variables to go along with this, so we're just going to leave it like this for now. What this does is it creates a function or a block of functions that will be associated with this. I make this public because I want to be able to access it in here. I want to make this public because I want to be able to access this function. We have this self variable here, and there's actually two selfs. There's a lowercase self and an uppercase self in Rust, and the uppercase self is basically saying return an instance of this data type. So to see what that looks like, we're gonna go ahead and nah, don't worry about it. Okay. Okay, and let's get rid of this, and let's say let hash. I'll call this hasher equal. Okay. Boom, 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 boom. All right, so what this does here is we're saying we're using the module here. I want to use this particular data type from this module. And then I make this variable called hasher. And that hasher variable is going to be a new SHA-1 data type. Now, I don't need to use new here. I can use something else. That's just common standard to use new. What new does, though, is returns an instance of SHA. So this here, this hasher variable, is this an instance of SHA? The type of it is SHA. You can even do, you could do SHA-1 here to show that this is a SHA-1 type. Okay. So that's it. This is the basic setup. We're gonna need to create a couple functions here. We are gonna end up changing that hasher to be mutable later. I'll talk about that in a minute. But for now, we want to start hashing. So as I said, if we pop back here, we are going to be sending this to our server, and this is just going to be a base 64 string, something, base 64 of something. So this key is going to come in as a string, and we want to be able to send that to our SHA-1 hash, our hash. We want to be able to hash it at some point. So what we're going to need to do is we actually need to create a function called hash. Okay, and hash is going to take in a string, which we call key. And you notice it's a string reference. We could probably just make it a regular string and be fine. And then we have a mute self. Now you notice this is capital S, and then we have a lowercase s. Capital S is referring to an instance of that data type, so it's referring to a SHA-1 data type. This self is referring to whatever instance of the data type that we're using. So when I do, for example, hasher.hash, and I send in some string, okay, we're going to get an error here because this is not mutable. Okay, so as I said, mutable, there we go. This mute keyword, if you're not sure what it means, it is just saying that this variable can be modified in some way. If we remove this, it's saying that hasher is immutable, which means we can't make any changes to hasher whatsoever. You might be saying, well, it doesn't look like you're changing it, you're just calling a function. And that's true, but here I use this mute self in order to be able to make changes later on. I don't technically need this. I probably could get rid of this and this would work just fine, but for the time being, I'm just going to leave it because I think later on we're going to need it as mutable. I think it will complain if it's not. Actually, you know what? Let's set it to be this, and then if it does complain, we'll worry about it later. All right, so in here, we no longer need this as mutable, so we're okay. But the mute keyword basically says you can change something, and if it's not explicitly defined as mutable in Rust, it is immutable, which means you cannot change that value. All right. So let's go on. Right now it's complaining because we haven't returned anything. If you come over here, you see we're going to need to return an array. This is an array of unsigned 8-bit integers, aka bytes, and then we're going to return 20 bytes. All right, so the end result for us is a hash, which will be a string of, or basically a string of 20 bytes is what it ends up being. Okay, so that means 20 characters of some sort. All right, now, in order to do the hashing, we need to do a couple different things. First thing we need to do is we need to implement some padding for our initial value. And by padding, I mean basically do some pre-processing on this string here. So this string, we need to do some setup so that we can actually effectively do the hashing. And the padding is going to pad things out so we get, well, you'll see in just a minute. But basically the goal is to give even chunks of data we can work with. And to do that, we could probably do it right here, but I want to create another function for it. So I'm going to create this, try to create some things a little bit, divide things up a little bit. We're going to keep getting this error until I fix that in a little bit. But for right now, we're just going to worry about this padded message. Actually, I think I can probably get rid of it. Let's let me grab. I think I can just let's just say let temp return equals u8 20 and then temp return. All right, cool. So now I won't complain. We'll just leave this here. This is just garbage. You'll notice a kind of interesting thing about Rust is you can return things without writing the return. I mean, I can do this, but I don't need to. I can just do that and not put a semicolon on the end and it will return. All right, but let's do this now. So we're going to take this string, and the first couple steps we're going to do, I'm going to pop back here so you can kind of get a better overview of it. Is where are we at? Start building. Yep. Here. All right. We're going to take this input and we're going to split it, the input to be hashed into a byte array. We're going to get its length. We're going to append something. We're going to pad the array with zeros, and we're going to convert the integer from step 2 and extend the array. These 5 steps, they're really simple. They're actually, they don't require a lot of work, but you might by the time we're done, you're going to go, why are we even doing this? And I'll explain why in just a minute. One thing I did kind of skip is what a hash is. A hash is basically a way in order to take some giant chunk of information or a small chunk of information and get out a fixed length string. So, for example, no matter how big these documents are, they're going to give you the same length string out. In our case, as I said, it's 20 characters. So we're going to have 20 bytes, 20 character string. That's going to look something like whatever. We don't really know what it looks like. These are, I think I wrote them in hex or something like that, but they could be anything. The data that's output is always going to be 20 characters for SHA-1, no matter how big the document is, which seems a little weird that you can change the size of the input and get a fixed length output, but we'll see that it's actually not too difficult to do. All right, so let's move on here and pop back here. And let's take this initial key that our client is sending us and let's do something with it. So to do that, I am going to go ahead and call this function, and I'm going to pass in string to it. Oh, sorry, I'm passing key to it. And let's do some work. Okay, so first thing we need to do in order to do this is we need to convert to a vector. So we're going to take our input, which is a string, and we're going to convert it into bytes, and then we're going to convert that to a vector. The reason we're using a vector and not an array is because a vector is going to allow us to add on additional items and kind of extend it without having to resize the things like we would have to do with an array. All right, the next thing we're going to do is we're going to save this off for just a second. So this is kind of saving the original bit length of our, well, the original bit length of this input. Notice this is the bit length, not the byte length. So we take how many bytes there are, and we're actually taking it as a U64 variable. We multiply it by 8, so 64-bit unsigned integer. We multiply it by 8 because every byte has 8 bits, and we get the total bit length of our original message. Now that original message could be really, really big. It's kind of why we're using unsigned 64 as opposed to a U32. Next thing, we're gonna take this here, this byte array, and we are gonna loop over it, and we're going to add on zeros until we get to the point where we are close to being a block of 512 bits, but we're going to be 64 bits short. And we'll see why we're going to be 64 bits short in just a minute. Don't worry, we're going to take a look at what these actually look like. I'm going to throw some print lines in here. We'll run through an example, and you can kind of see what it looks like. And then the last thing we do is this. Okay, we are going to take this value here, which is going to be a 64-bit number, and we are going to append it to the end. So this here gives us 64, and this is missing 64 bits. So at the end, what we get is a whole bunch of, basically we get a list of bytes that is modulus 512, okay, as far as bits go. That means when we go through this, we're going to be taking out 512-bit chunks of data one at a time. So the resulting vector, okay. Oh, why are you complaining now? I just fixed you. Oh, we need to initialize this. Let me see if I can remember here. get it initialized with zeros. I'm trying to remember off the top of my head. There's a way to initialize something with all zeros. I think I can just do this. Yeah, there we go. All right, cool. There is a thing called unimplemented, but we don't want unimplemented. Unimplemented would let us basically, we're not implementing this function, which fortunately means we're not going to really get anything, be able to run it here in just a minute. All right, so let's walk through these steps again. We take our string, we break that string down into vectors, into a vector of bytes. We get the bit length of the array. So say we had 1,000,000 bytes, we'd get the bit length of that, and the bit length of that would be 8,000,000 bits, and that value 8,000,000 would go into this variable original bit length. We then loop through the bytes array, and we're going to keep adding on zeros. We're padding it on the end with zeros. Okay. I think I forgot something here. I did forget this very important bit. I just realized. All right, so one thing I forgot. We need to push this on. This is the delimiter between our original data and the padding in the end. So we need to push on this. This is what this looks like is this. It's basically leftmost significant bit 1, everything else zeros. So what we end up having is we have our bytes. Okay, and then over here we have our padding. Okay, so that's what that looks like. Sorry, forgot to put that in. We're gonna loop through all of this here, adding on all that padding. And then at the end, we take that original bit length and we also append it onto the end. Okay, so the end result of this is going to have that padding, and then at the end, you'd have that bit length. Okay, so this is basically what happens here. All right, so let's get rid of that. Maybe put that down here. All right, cool. Now we then return those bytes. All right, so let's take a look at this so we can actually see what's happening here. Let's go ahead and add a print line. I'm just gonna make these all debug statements because some of them will require it, some of them won't. Original bit length. Do bytes again, bytes again. Okay, so we can see what this looks like. We can just do cargo run. And what we're going to see here, and let me scroll this down a little bit so you can see. This is the original bytes, and it's just coming from here, testing. So testing has 8 letters in it, so we get 8 letters. These are just the ASCII values for those individual letters. This is the bit length of that, so it's 7 times 8. Then we append 128, which is the same as this value in hexadecimal, which is also the same value as you can see here if I hover over it, of 1 with 7 trailing zeros. We then pad this out, and when we pad this out, we are going to get 512, well, almost 512 bits of information. We're getting everything but the last 8 bytes or 64 bits onto it. Now, we only have this one chunk of data, but this here can be a whole document. It could be a gigabyte of information. It doesn't really matter. And in fact, like hashing is used in order to verify information, because as I said before, you put the same data in, you're going to get the same number out from a hash. So for example, if I put testing in again and I run this again, it's always going to give me the same data. And when we're done with the hash, it's always going to give us the same data. All right, so here we're going to extend this until we get to the last chunk of all of these. So imagine if I had a really large document, this might be the last chunk of many other 512-bit or 64-byte chunks. And then we take the value from up here, convert that, and we get this. So you're going to see this says 56 because I have 56 here. The other ones are just going to be empty. If we had a larger document, this would be a larger number, and the bytes, if it was more than 255, we would see this. In fact, let's do that. Let's make this a little bigger. Let's just do this here. Okay, that's probably going to be enough. Cargo run. You're going to see that now we're up to here, and we've got 2 here, and we got 72 for the first byte. This is not 272. This is, 2 converted for the second byte and 72 for the first byte. All right, so you can do the math on that if you want. Let me back this up to make it a little more simple. All right, so the padding is pretty much done. We have returned this. I'm going to take these print lines out of here for right now. I think that's it. I'm going to clean this up a little bit. All right, good. Let's go up here. And we've added our padding. Leave that comment, it's fine. And now we want to do the next step. All right, so this padding of the message, it looks kind of like we've done something, but really all we're doing is setting it up for the next step, which is actually the SHA-1 algorithm. All right, so let's grab this and take a look down here at those steps. Boom, 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 boom. All right. Oh, I missed it. Okay. Oh, no, I was right. Step down, I think it's step 6 or so. All right, so this is also known as the schedule. The schedule, message schedule. We're taking the message and we're building a message schedule. I don't actually know why it's called the message schedule. I'm sure there is a historical reason for it, but whatever, I'm not exactly sure. Now, these constants here, these are taken from the fractional part of some square roots, the first 5 square roots. So this is the square root of the decimal portion of the square root of 2. This is the decimal portion of the square root of 3 and 5 and 7 and 11 respectively. All right, so we can actually take those and we're going to put those in up here. Let's put those all the way at the top, some constants. Okay, and we're going to be using those later on, but we're just going to put those up there for now. Okay. And these are the steps. This is a lot more steps than we had before. Let me try to shrink that down so they're not overlapping too much. These are the steps we had before. Some of these steps take a lot of work. Some of them are very quick. So for example, 10 and 12 are just telling us we're going to repeat something. These are parts of loops. The other steps, they could be making an array of integers, but then there's steps like step 7, which we're going to spend significant time talking about. All right, so let's take a look at the first part where we are going to build, make some copies of some variables. Okay, so this here, I'm going to go ahead and add some variables here. I'm just going to pop back here. We're going to pop back up to our hash. And I'm going to add this in here. I'm actually going to put it before the padding. This doesn't matter. You can put it here. You can put it here. It has no bearing on what we're actually going to be doing. All right. So we do that. And these are going to be accumulator values. So when I say accumulator, we're going to be continually adding onto these as we go through new values as we do our hashing. And actually at the end, we're going to take H0 to H4, we're going to smash them together, concatenate them together, and we are going to get our final result. So each one of these values, okay, each one of these values is, if we put them all together, we should be able to get 20 bytes of information. If you do the math, we have 5 values here. So each one of these is an unsigned 32-bit integer. So they're each 4 bytes. Okay. The next thing we want to do is we're going to start our loop. Now, if you're following the tutorial, We don't mention that we're doing following that listing rather. We don't mention we're doing a loop, but until later. But this is what we do. We take our data, the message that we have made, and we're going to loop over it in 64 byte chunks. And that means it's 512 bits. 64 bytes is 512 bits. As I've been mentioning, we're going to take those in chunks. And we know, because we did the padding, that we can get exactly an exact number of 64 byte chunks. So there's not an extra 1 byte at the end or anything like that. All right, so we're going to do this. We're going to do it for all of the chunks. We're going to use this chunks method, which is part of vectors. It takes the chunk out for us, so that's nice. So this chunk is going to be 64 bytes or 512 bits. The next thing we're going to do, and you're going to see that I am using self here and self here. So as I mentioned before, this self is for the instance of this hasher here. So what I'm doing is just using this self to call these functions given the information that I passed in with, perhaps passed in, or that's attached to that particular instance of our SHA-1 algorithm. That would only matter if we had variables, really fields we were manipulating in there. We don't have this yet, so we're going to go ahead and create it. And normally you're probably not going to be creating functions for something like this. You don't want any additional overhead of anything. So you just cram it all into one function. I'm only doing this because it makes things a little bit neater for us. All right. And we're going to be doing this build schedule here, and then we're going to return it at the end. So there's going to be a few things. Why is this complaining? Oh, can't borrow. All right. So remember what I was saying about borrowing as mutable? It cannot borrow this as mutable because I'm passing in that chunk like that. So let's go back here, and we're going to make this mutable. And come back here, and we should be good to go. All right. The next step for this, as according to the listing, I'd probably just keep that list from over here. Just keep this here. So we're on this, take a single chunk of 64 bytes from our message. That's where we're at right now. So we're going to take a single 64 bits from message, make sure here. Okay. All right, so we're going to take this. Yeah, okay. So we're going to be pulling from this chunk here. These chunks are going to be in bytes. Okay. And let's see here. Create this, then we're going to be pulling these chunks one at a time. So this schedule, what it's going to be doing is we're going to be taking this array, which is empty at the moment, and we're going to be filling it up. At least the first 16 unsigned 32-bit integers are going to be from our data. All right, so we're going to 64 bytes of information, which is one chunk of information, is going to be shoved into the front of this array. Okay, and that's exactly what we're going to be doing here. We take out one 32-bit integer or 4-byte integer out at a time. We shove it into this array, and that's it. We're going to do that because the next step is to take those first 16 bytes, and we use those first 16 bytes to now create the 17th byte and a 17th unsigned 32-bit integer. So we're going to keep adding integers into here, one integer at a time, and we're going to be using our previous values in order to do so. So when we start this at 16 because 0 to 15, that's our first 16 integers. And then 16 up to 80, not including 80. And this ... is the same thing as a range or something like that in another language, or for int I equals 0, I is less than 80, I plus plus type thing. And we're going to index here, and then we're going to be doing this. This operation is an XOR operation. It's a logical operation. If you're not sure what logical operation it is, then go check out what XOR does. It's basically an exclusive OR. It says that, based on what one bit is and another bit is, if there are, say we have a 1 and a 1, and we do an XOR, we get a 0, and a 0 and a 0, we get a 0. If we do a 1 and a 0, we get a 1, because the 1 and 0 are different. That's what an XOR means. It's basically, it's true if the two inputs are different. Now this does what's called a bitwise, because we are pulling out entire bytes of information, or you're pulling out entire integers worth of information. And any chunk of information, it will just go through and bit by bit for each one of those do an XOR operation on each one. So for example, if I had say I had 1 0 0 1 0 1 1 1 0 0, it would go through and do 0 0 first. 0 0 is the same, so we get 0. 1 1 1 0 is different, so you get a 1, and 0 1 is different, so you would get a 1, and 1 1 is the same, so you get a 0. Okay, that's basically what it's doing, and it's going to be XORing all of these previous values together. So it's taking our data, so whatever we typed in, testing for example, it's converting everything to binary, and then it's just gonna start smashing those binary values together in order to create some more information. And then we take that whole thing and we rotate it left. So a rotate left means if I had something that looked like that and I rotated it left, it would now look like that. If I rotated it left again, I would now get that. It's basically taking the leftmost bit, shoving it to the right side, and moving everything over a little bit. Okay. All right. So that sets up our schedule, and we have now completed this chunk. At this point, we actually have some scrambling of information. It's kind of scrambled. We've gone through each of these, and we've basically taken previous values and smashed things together. Unfortunately, at the start of each one of these, we still have the original data, so we haven't really done enough obfuscation in order to hide the original data. So you could easily work your way back and figure out what the original message was. The next step is going to take care of that. So what we're going to do is we're going to loop over every integer that's in this schedule, and we're going to perform an operation on it. And this operation is a little bit confusing. Okay, a lot of bit confusing. What we have here are a number of different calculations based on which set of values we're looking at. So 0 up to 19, including 19, we do one thing. 20 up to 39, including 39, we do another thing. You're going to notice we have a few things undefined here. That's because I haven't added this in. What we have here, remember H0 to H4, this is the value we're going to be adding on as we go through. A through E, these are the values of just one iteration. So we're going to do these calculations. This A through E is going to get added on to the H through 4. So we're going to take these, do some calculations, get a result, and then we're going to add them onto this in the end. Okay? So we're also going to get a few errors here. These errors will resolve themselves very shortly once I put in some more code, so you can ignore them for now. But what this is, this match statement, it's pattern matching. You may have seen something similar to this before. It's kind of they're borrowing it from functional languages. There's other languages that have similar things. Even a select case is kind of similar to this in a way, but this is much more powerful. You can do lots of different things with a match statement. So for example here, this is matching from 0, as I said, to 20. The first 20 items, the next 20 items, next 20 items, and then whatever's left over. All right, so this is the default thing here. Underscore just says everything else do this. Whatever the result of the match is needs to, if we have a let over here, so let this tuple or tuple, whatever you want to say, match these two values at f and k. We haven't, this is what we call the function. This is called a key. You notice that there's a calculation, a function on the left side of this in here, and then the value on the right side is a constant. And this constant is just another one of these values that they're using. These are going to be, I believe, 2 to the power of 30 times some square root of, let me double check that. It's like, yeah, let's see. 2 to the power of 30 times the square roots of 2, 3, 5, and 10. And that's where those come from. Okay, so these values, don't worry about them. They're just there in order to make things a bit more random. What we're going to do, though, is these logical operations, which have different names. This is going to be, if you take a look here, I do have them listed. We've got a choose, a majority, and parity. And you can take a look at what those mean if you like. What they are here is this is choose, this is parity, and this is parity. The parities are using these XOR operations. The choose is picking one or the other value to return. And sorry for the pop up there. The last one here is going to be combining multiple ones together. It basically says it takes the majority of 3 different variables, B, C, and D. So we get these values back, this f and this k, and then we're going to need to do something with them. And the first thing we're going to do is we are going to combine most of them like this. So we create this temp value. We're going to take A, so we're starting with A, and this is kind of how we're diffusing the information through all of our different variables, A through E. And we're going to be doing this multiple times as we go through. And because we're going to be adding on to, we're going to be modifying A through E as we go through this inner loop here, this 0 to 80 loop, as opposed to this big chunk per chunk loop. And we're going to be doing this. And this is, I'm not 100% sure on the rationale behind all these things, but I can give you a general idea of what's happening and why it's happening. So I can't, for example, tell you why do we add these in this particular order and why are we adding this schedule I at the end? I'm not sure. But what I do want you to pay attention to is the way that the values are changing. So for example, we change A, we save this A off, and A gets changed significantly because we're using this F and K value as we go through here, including the schedule value itself. Then in here, we basically are taking, D becomes E, C becomes D, B becomes C, A becomes B, and then temp gets put into A. And we're going to be doing this loop 80 times. And as we go through, the changes from A are going to be moving up through these because A is basically replacing these values as you go. So the change starts in A, and then it replaces everything as we go up, with this one exception here where we rotate left 30. Again, not entirely sure why, but that does significantly change a value when you rotate something. And as we've talked about before, rotating is just shifting bits and wrapping back around. Okay, so A changes a lot, and then each one of these values ends up being slowly replaced by those. And then at the end, we take whatever's in E and we shove E back in here as part of the wrapping add. So it's kind of like a circular diffusion of information. Information from each of the variables is being pushed into the other variables. Even B will eventually, because B becomes C and then D and then E, B will become part of A number of iterations in, and then A gets put back in, and then we continue that process. So this process is kind of, what it's doing is it's spreading this mixing of the data across all of these 5 variables, A to E. And that's really important in hashing because you don't want one variable or changing one portion of one variable to affect any other portion of your end hash more than the other portions. If it does that, then there's an opening for an attack where people can start tweaking part of that input or part of the hash in order to kind of figure out specific areas that it's going to change in the hash, and then you can end up breaking the hash eventually and making it useless. All right, so take a look at diffusion and confusion and diffusion, diffusion and confusion. There's a link in the article. You can also just look it up and find the Wikipedia page, and it will go into more detail on these two aspects of hash algorithms and why they're important. All right, so once all of this has been completed, once we've done this inner loop, as I said, we're going to add some stuff on here. We're going to add on these end chunks, and this is our accumulator values here. We're going to add that in, and then pretty much we just do that. We do that for every single chunk we have. So if we had, 1,000,000 64-byte chunks or 512-bit chunks, then we just do it for every single one of them. And when we're finally done with all of those, we are going to end up combining whatever is left in h through 0. We take this h through 0 hash, we copy from these slices to get that, and then we can return a hash. And I'm looking at this now, I'm pretty sure might be an easier way to do it, but for now this works just fine. Okay, so we can actually now get rid of this, and we're actually done. This is it. This last part, hopefully just easy. We just create a new hash. We take all of these individual chunks that we had. Remember, they're each an unsigned 32-bit integer, or they're worth 4 bytes. So 4 times 5 gives us 20 bytes, and we return the hash of 20 bytes, just like we said we would at the beginning. And if we run this, so what we need now is we're going to need, say, we'll call this let result, and we'll print, I think we can just print that. Nope, I guess we need to, here we go. We will get back an array, a vector of byte values. So let's run it. Let me clear this, cargo run, and here we go. This is going to be 20 integer values, or 20 bytes, and this is our final hash value. And we can convert that into whatever we want. We could turn it into a string. We could cast them to ASCII values and plug them together. You're probably more used to seeing them concatenated as ASCII values, but here we'll leave it as the byte array. And in the next video, we're going to actually convert it, and then we'll send it out as a base 64 encoded string. All right, so this is not the easiest tutorial, I don't think. I hope maybe you learned something just by watching it. If anything, you got something through reading the article or just going through the repo. All right, thanks for watching. If you have any questions, leave them in the comment section below, and take it easy.